let's continue with multicast, and this time we will dig deeper from the L3 side, right? Till now what we have done, we have looked into the introduction piece, why we need multicast, various components of it, how multicast mainly works with respect to IGMP protocol, right? Then we talked about the IGMP snooping, which is kind of like, you can think of it as a multicast functionality at the layer 2. But now we'll switch gears and we'll move to L3, right? Multicast routing. Now, routing, when you talk about routing, right, what is it basically? At the end of the day, you have a router, you have another router here, and you basically have some outgoing interface, right? This is 0/1, 0/0, whatever, and you have a subnet 12.0, and I don't know what this is. This is probably like 2.2. Let's say this is the loopback over here. Okay, so on my R1, if I want to send a packet towards this 2.2.2, right? So what we have to do, R1 is going to receive the packet, then it's going to look at the destination address, which is 2.2.2. Where it is going to look, it's going to look in its routing table, and from the routing table you're going to have an entry saying, you want to reach 2.2.2, take this interface, which is FA 0/0, right? And then it's going to forward the packet along that interface. That's your literally routing in a nutshell. But then how would routing work in a multicast scenario, right? This was unicast, but routing in a multicast scenario, so if I have something like a video server, I've been using video as the only example, but don't think that multicast is used only in videos, right? You have the video server, think you have router 1, router 2, right? You have unicast routing here between all of these guys, right? Probably, I don't know, maybe 192.168.1.0. This is 192.168.12.0, right? And you have the same, loopback here, 2.2.2.2. Now, how is the packet going to be different in case of multicast routing, right? So the packet which is going to be coming from here, right? The destination, in fact, the destination IP address is going to be something like, the group address, right? Which is going to be something like 239.1.1.1, right? That's going to be a destination IP address, right? Now, when the packet comes down here at R1, the R1 will obviously not find this particular IP address in this routing table, because the routing table, whatever we have seen till now, that was unicast routing table, right? So this particular IP address it's not going to find. So you can't literally use your unicast routing for forwarding packets. So you want a different kind of a routing protocol, and that's the need for having your multicast routing protocols. Now, when you talk about multicast routing protocols, right, there are mainly two of them, famous ones, your dense and sparse, right? So there are two types, your dense mode and sparse mode, right? Now, again, under this, you have different types of protocols, like, PIM is very popular, very widely used, right? Protocol independent, it's a PIM, and then you also have things like, I think multicast OSPF is there, you have distance vector multicast routing protocol, and so on. So there are a lot of routing protocols, but then the most common one and the ones which we are going to discuss is also the PIM, right? So we are going to discuss the dense sparse mode in detail. Obviously there's one more mode called as sparse dense mode, which is kind of like a combination of both, which is probably something interesting that we'll do that at the end of the session. But for now, to start with, let's look into the dense mode. So we know why we need multicast routing, right? Why we need that, and we have different types. So let's pick the first one, which is our dense mode, right? All right, so I have a separate picture for that. Yeah. So this is the topology which we'll be using in our lab to kind of do all the packet captures and all of that, right? But to give you an understanding about what dense mode is. So in dense mode, what we do is, this is my video server here, right? I have my routers R1, R2, R3 over here, and these are my host H2 and H3 connected to them, right? So in dense mode, right? Or just to again double click on, because when you're reading about dense mode, it's always good to know what is sparse mode as well, just so that you can compare, while understanding. Dense mode, always remember, we use a approach which is like a push approach, right? So we push the multicast traffic on all the interfaces in dense mode, right? We push it on all the interfaces, in dense mode, until a downstream router, say someone like, until a downstream router, my bad, not the client, right? Until the downstream router basically tells that, okay, I don't want you to send me the packets, right? I don't want you to send me the multicast data in this particular path, right? So until someone, downstream basically tells me, I'm going to forward it, continuously on all the interfaces. I'm going to flood it on all the interfaces except the interface from where it came from, right? So that is your dense mode in short. Sparse mode is basically where we don't forward multicast, or we don't push multicast traffic on all interfaces until a downstream router, will proactively or will explicitly request for it, right? So downstream router like R2 is going to explicitly say, hey, R1, I'm interested in the multicast traffic, please send it to me. So that's the main difference between a dense and the sparse mode. In dense, we basically push it in all, kind of all interfaces, whereas in sparse mode, we pull it, right? We pull, because I'm just saying it as pull because R2 is the one who is the downstream router. He's going to request saying that he wants the, traffic for that particular group. Now we'll double click more on dense mode now. All right. So to do that, just pick the diagram. Maybe get rid of this. Okay. So let's imagine we have the let's get the pen here. Yeah. So we've got the video server right over here, and the video server is sending multicast packet towards R1. Right, in this direction. This is a better color probably. Yeah, R1. As soon as R1 receives the multicast packet, it will create an entry in its multicast routing table. I'll show you that in the lab, where it stores the source address, right? Basically the source address of my video server, which is S1, and the multicast group, right, for which this guy is streaming, say 239.1.1.1. Once it does that, then it will flood the traffic on all the other interfaces except the interface from where it received. So it is going to flood in this direction as well as this direction. Now this one really creates a bit of problem. If you look at it, what is going to happen is, imagine R1 sends it in this direction, right? This guy receives it, R3 receives it, then R2 can then forward it in this direction, right? Now R3 can take the same packet which is receiving from R2 and send it back in this direction, right? Now what's going to happen is this packet is going to circle around here, and at the end of the day it's going to create a loop, right? And we really don't like loop. So to get away with loops, right, we have a very interesting mechanism which is put in place, right, to prevent that. So I like to call it this three-step process here, right? So there are three steps which happens whenever a router has to forward packets in case of PIM dense mode, or basically your multicast, right? The first step is your RPF check. Now RPF stands for reverse path forwarding, right? So how does RPF work, right? Let me just get rid of this once again, right? So how does RPF work? So imagine your R3 has received the packet both from R3 has received it from R1 as well as it has received it from R2 as well, right? So this guy has received now 2 copies. So he has a decision to make. What decision? Which packet to accept and which packet to drop. How is R3 going to make that decision? So R3 is going to look at the multicast packet, and it is going to look at the source address in the multicast packet. The source address is S1, right? So it's going to look at the source, and it's going to try to find, this is the source address, right? And it's going to look at its unicast routing table, right? So that is one of the reason you call it as PIM, right? Protocol independent. So it doesn't depend what unicast protocol you're running, but it is obviously, it has to be, that particular route has to be on the routing table, So it's going to do a RPF check and it's going to find out that this particular source, which is S1, is present in the routing table and which is the outgoing interface for reaching S1. So if I had to send a packet in the reverse direction, right, from R1, imagine if this was the path. So obviously the entry is going to be Ethernet 0/0, right, this entry. So as a result of that, this packet is accepted, whereas the packet received from R2 is dropped, right? So that's your reverse path forwarding. So that's the algorithm which is going to be used, right? So that's basically how it works. So R3 is going to receive, and obviously when I say drop the packet, it is also going to send a prune in this direction. So there is another packet in case of PIM dense mode called as the prune packet, right? We'll see this in our packet captures, but it's called as prune. So when you're sending a prune, it basically means that you'll send it to upstream routers, and when you send a prune, you're basically telling that guy R2, please don't send any more multicast packets along this particular path, right? So that's why you're sending a prune in this direction towards R2, right? And once that is done, now it is free to forward. R3 is now free to forward, the packets in all the other interfaces where it did not receive the on all the interfaces except the interface on which it received. So in this case, it's going to forward it on Ethernet 0/3, right? So that is one part of it. So if you have to call it the 3-step process, the first check which is done is the RPF. If RPF succeeds, right, then we go to step number 2, right? If RPF fails, then along that interface we send a prune, right? Step number 2 is basically, like I said, forward, on all the ports except the port from where it received. Step number 3 is nothing but the downstream routers now will try to look at the packets which they have received, and they will see if there are any clients which really want this stream, right? So here in this case, let me again get rid of this, right? So here, imagine we have something like this. We have H2 which is interested in 239.1.1.1, whereas this guy is not interested, right? So the multicast packet would have come here, would have gone here, and would have gone to H2. At the same time, it would have come to R3 and it would have gone to H3 as well, right? So in fact, sorry, it would have not even gone to H3, right, because it is not interested. So R3 will figure out that there is no one who really wants this multicast group, or there is no one connected to him who would be interested in the multicast group, right? So he is going to take the decision and is going to send a prune in this direction, right? The prune which we talked about, it's the same prune which is going to be sent in this direction. So now R1 knows that it shouldn't send or it shouldn't forward any multicast packets in this direction. As a result, now the only packets which are going to be flowing in the network are going to be only in this direction, right, from R1 to R2 to H2. So that's your dense mode, literally, right? So going back to this, the first is the RPF check is going to be done. If RPF check succeeds, then you're going to forward it on all the ports and flood it on all the ports except the port from where you received. And downstream routers, they'll start now analyzing, and they will see that, if they don't have any interested candidates, right, for this particular multicast group, they are going to send in the prune packets. And that way, so initially there'll be a lot of churn in your network if you're using dense mode, but after some time it will go and get stable where, now you see only these guys are interested, or only the packet forwarding is going to happen only here, right? So hope that was clear. So that's literally your, let's see if I have to cover anything else, right? So yeah, so that's mainly it. Okay, there's one more thing. Just get rid of this again. Right, the other thing is, now once this path has been achieved, right, it has decided that, I have to forward to R2 and R2 has to forward to the client or the application, whatever it is. This topology, whatever you see here, right, that's basically called as a shortest path tree. You'll hear this term quite a lot, shortest path tree, or SPT, or in short you can also say source tree, right? So you can call it as shortest path tree, or you can say source tree, right, either of them. So why you call it as a tree? Because the tree defines the path from where? From the server or from the source to the destination. So that's why you call it as a tree. the source for the source will be the root of the tree. So this guy is the root for this tree, right? Source tree. You call it as source tree. So source is nothing but the root of the tree. The routers in between, in this case R1 and R2 are basically the nodes, right? And the subnets, let's say in this case 192.168.2.0, whatever it is that, the subnet over here, right, they are basically called as the leaves or branches of the tree. So in dense mode, the only tree which you will come across is the source tree, right? So depending on the source and the multicast groups that we use, you might have come across, you will basically come across, the notation which is S comma G, right? So when you look at the routing table later, right, the multicast routing table, you will basically start seeing the S comma G notation, because this is the notation which is used for defining or for representing that particular tree. So here in this case, the S comma G is nothing but going to be, the S is nothing but S1, right? That's the source IP, and the group is say 239.1.1.1, right? So this is your S comma G. So that's a notation just for representing that tree, right? Cool. So that being said, let's just take a minute to get rid of all of this, and we can go down to the lab and see some cool packet captures, right, to make sense of whatever we talked till now. Alright, so hope my lab is up. Let's get the lab up here. So let's keep it beside this to look at the topo. Yeah, it looks good. Awesome. So we'll start by what? We'll start with enabling what? The unicast routing, right? Like I said, we want unicast routing here. Without unicast routing, it would not work. So you really want the unicast routing to be configured, because like we discussed, right? You especially for the RPF, right? You need to have the unicast routing enabled. So let's see what is already there. I have already configured OSPF everywhere. Show run section router, right? So don't I have OSPF? Interesting. Okay, I think I have not configured then. Probably I put only the IP address. Okay, so I have not configured OSPF. We'll configure OSPF. So the first step is to go and configure OSPF, which means let's go here, router OSPF 1. Let me just give me a minute. Alright, so router OSPF 1, I'm just gonna put 1.0, 12.0 and 13.0, because those are the subnets connected to me. Right, this is 1.0 towards S1. Between R1 and R2 it is 12, R1 and R3 it is 13, right? So so I'm basically gonna enable OSPF over there. This is the topology, right? Let me just show you here. So between this is your 12, this is your 13, and this is your 23. Pretty straightforward notation, nothing complicated. Let's go to R2. Let's enable there as well. Right, so here it's going to be 192.2.0, 12, and I believe 23. Let's go and enable that. There you go. That's your OSPF on R2. And on R3, it's going to be 3.0, 23, and 13. So let's pick that, and there you go. So let's go and do that. Awesome. Yep. So all my routing is up. You can see my OSPF neighborship forming here. Let's wait for a second. I think it's good. Let's quickly check show IP route. Yep, I have my routes, I guess. I have 2.0, 3.0. Perfect. Everything looks good. So once you have the unicast routing, it's time to go and enable multicast routing on all the three guys. So let's go and do that. Okay, I made a mistake over there, but anyway, let's enable on this guy. Let's enable on R3. Let's go back and enable it on R1 as well. Alright, so we've enabled multicast routing on all the routers, concerned routers. What do we do next? Let's go and enable the PIM dense mode under the interface, right? Let's do it on one of the interface, which is my Ethernet 0/1, right? Let's do it on that guy first, right? Let's go to Ethernet 0/1 on R1, and we are going to do IP PIM dense mode. There you go. As soon as you do that, we should start seeing some hello messages here. Let's refresh. Let's see the capture. And okay, maybe I think this is the interface. I'm not sure. Let's see. Yeah, there you go. Right. So you have the PIM hello messages which are generated now. Right. If I look at the PIM message here, you can see hello. Right. And look at the destination address to which this hello messages are sent. It's 224.00.13. Right. These are again standard. Just like how we talked about the membership query messages sent to, I think, 224.0.0.1. Similarly, you have this being sent here. Right. So let's go and enable the same guy on my other side, which is I think on R2. Again, it is on the same interface Ethernet 0/1, and let's enable, sorry, my bad, 0/1, and we should do IP PIM dense mode. There you go. Right. So as soon as you do that, you can see the PIM neighborship comes up between R1 and R2. So we have enabled it between R1 and R2 now. Right. So let's do the same thing for all these interfaces. So on R1 we have to do it for 03 and 00 as well. Right. So Ethernet 03. Let me just grab this from here. And I'm just using a notepad on my other screen to create the command because it will be easier to paste quickly. So 03 and the other one is 0/0, right? Yeah. So let's pick this. I'm going to paste that now on R1. There you go. So on 03 and 0/0 we have enabled. Similarly for R2 we have to do it on, we have done it on 0/1, we have to do it on 0/2 and 0/3. So let's pick that and let's go to my R2 and do it here. Awesome. So that's done. And on my R3, I gotta have it on 00, 02 and 03. So let's copy that onto here. Right? There you go. So I've enabled PIM dense mode on all the interfaces on all the routers, which means we should start seeing some cool stuff like, go to R1, show PIM neighbors, right? You can see the neighborship has formed. R1 has formed PIM neighborship with 2 and 3. Similarly, yep, there you go. So we've got between R1 and R3 and here as well. On R3 as well, it looks good. Now we'll start with the cool stuff. So multicast routing. What is the command to check the multicast routing table? That is, it is nothing but show IP M route. Just like your show IP route, just put a M in before it, M prefix it, and that becomes your multicast routing table. Right? You can see have a lot of flags up here. Right? So all these flags basically correspond to, you'll start seeing those flags down here in, across each of these routes, right? Now for now, what you see here, I'm basically showing you the routing table of R1. Let's just concentrate on the D flag here, which is the dense flag, right? So at this moment, we don't have any multicast traffic going on, but we do see a multicast group in the table, right? We see this, right, in the tables for 224.0.1.40. Now this can be a bit confusing, right, if you are new to multicast, because this corresponds to the auto RP, which is a feature under PIM sparse mode, right? So a quick understanding is that the PIM sparse mode uses rendezvous points, right? And Cisco routers support a protocol called as auto RP to automatically find the RP in the network. So auto RP uses the multicast address, which is 224.0.1.40. So PIM dense modes doesn't actually use any kind of RPs. right? So there is no reason for us to worry about this entry at all, right? So any messages or any entries corresponding to this address, just ignore it for now, at least for our dense mode discussions, right? Even if you look at the interface here, right, it basically tells that the interface is null, right? The outgoing interface is basically stopped, right? So it doesn't have any relevance in our discussion because it is mainly concerned to the sparse mode, which we'll cover later. It's enabled by default, so that's why you will start seeing this. That being said, let's now, what we'll do is we'll go to one of our hosts, right? H2, H3. Let's go to H2, and what we'll do is let's go to the interface Ethernet 0/0, and on this interface let's try to join something. Let's try to join. By default, remember, our IGMP is using version 2, right? So we are going to continue using version 2. So using IGMP join, right, I'm going to join a particular group, 239.1.1.1, right? And as soon as I join, what should I see? So I joined, from H2 I joined. So let's see what has happened on R2. So on R2, you'll start seeing some cool stuff. Look at here. So on R2, we are seeing that we have an entry for 239.1.1.1, right? I mean, you'll still have the other entry which I talked about, right? Let me show you, right? You'll also have the 224.0.140, but like I said, let's ignore this. So that's why I just use the filter to just show you the entry corresponding to 239.1.1.1, right? So R2 has created, right? In my explanation I was telling, right, when you get any kind of because here, this H2 is trying to send a membership report, right? Or it's trying to use IGMP to join a particular group. H2 is trying to join 239.1.1.1. So when that packet comes to R2, it is going to immediately create an entry, right, for that particular group in its multicast routing table. But at this point, we are not receiving any traffic for this group, so we don't know what is the source, right, for this particular group. That's why you have it as star here, right? So as a result, we can't forward anything. We can't forward packet. Let's change that. How do we change that? Let's send some data. But before that, let's see on our I think this one is my, let's see, do I see something? Yeah, so these are the hello packets. No, I don't think you should have one. Okay, this is good. So let's keep it this way. Let me just get rid of this. Yeah, let's keep it this way for now. And now, like I said, we don't have any traffic yet. So let's solve that problem by creating traffic. So let's go to the server. I'm going to create some traffic on my video server. So I'm going to say ping 239.1.1.1. Repeat it for a big value, something like 214760123, whatever, a big number, right? So now it is trying to send packets to whom? We have created the multicast source now. The multicast source, which is the S1, is trying to stream multicast packets, and look, the ping is successful. It is getting packets from 192.168.2.2, right? 2.2 is basically this guy, H2. So it is getting the response from him, right? So now let's try to look at each of the routers. So on R1, what has happened on R1? So if I do show IP route for this particular group, you'll see a new entry has come up here, and you can see it is no more star comma G like above. You have a actual source, which is 192.168.1.1, which is the actual source here, isn't it? Observe the flags. The flags are important. Where are the flags? Let's try to understand the flags. So let's start from top, right? We have to understand what is happening in these two entries. So R1 is receiving multicast traffic from for 239.1.1.1, right? From where? From 192.168.1.1. This is the source. On which interface? You get to know that incoming interface is Ethernet 0/3. It is getting it from here, and has added this entry on the table. So this is the S comma G entry that I was talking about before, right? This is the S comma G, right? So how long has it been forwarding the traffic? It has been forwarding it for like 38 seconds, right? And actually this one, right? It's been forwarding it for 38 seconds, and the timer is going to expire. The timer is basically set for 2 minutes 21 seconds, right? So this entry will be removed from the multicast table, after that, right? So as and when we are receiving the packets, this timer will be refreshed, right? So if you are continuing, that's why I created a huge. You see, I've created a repeat packet with like a million. I know, I think number is bigger than a million. So I've created a huge storm of ICMP, right? That's why I've created that, so that this entry doesn't get timed out. If I run this command again, right, you can see that it will basically go down to 0 and then it will refresh again, right? So that's pretty good. The next is, let's look at the flags, right? So here one of the flag you see is the T flag, right? So the T flag basically means that we are using the shortest path tree, SPT, or source tree, right? I explained earlier. You can see here T basically corresponds to SPT bit set. SPT is nothing but shortest path tree or source tree. Basically the path, right, has been established between the source and the destination. That is what it means, and we are using that tree to forward the multicast packets. You can look at the RPF check, right? You can look at the RPF neighbor for R1 is 0.0.0, right? Why? Because in this case the server is directly connected to R1, right? That's why it is 0.0.0. Got it? And what else? It is forwarding traffic on its which interface? Ethernet 0/1, right? Which is in turn connected to obviously R2. And also observe here, it has stopped forwarding packets on this interface 0/0. Here you can see there is a prune. Why? Again, goes back to what I was explaining earlier, because R3 doesn't have any active clients who wants this multicast traffic. We have enabled it only on H2. So R3 doesn't want, H3 is not listening to this multicast group. So R3 has sent a prune. As a result, the prune is visible here, right? I'm not sure if the prune would have been caught here. So let's check if the prune was caught. Let me do a PIM here. Do we have the, I see the hello messages, or maybe I think we should do it on this one. I think this is the capture for that. So let's see this. Oh yeah, see, I can see a prune message over here. There you go. So let's check the prune. Let's see how the prune looks. Look here, it says number prunes. Number of prunes is 1, and we are basically 192.168.1.1, right? So we have basically said this prune has come from where? It has come from 192.168.13.3, which is R3. So R3 has sent a prune, right, for this particular group, which is 239.1.1, saying that it really doesn't want the multicast stream for this group, right? So this pruning and flooding is going to continue, or it's going to happen every 3 minutes, right? So interface is pruned. Whenever I get a prune, I'm going to prune the interface for 3 minutes. And each time we, and after the 3 minutes, the timer is going to be resetted. And again, your R1 will continue forwarding, or will restart forwarding packets again. And then again, he'll send a prune. So this flood prune is going to continue like a cyclic, fashion. All right, moving on. Let's look at the same thing from a R2's perspective. Let's look at the routing tables on R2. Let's look at what has happened there. Where's R2 here? All right, so let's see on R2. There you go. So on R2, observe the flags here, right? So we have the flag called DC, right? And the T flag. T flag, like I said, it basically means that this is corresponding to your SPT, right? This is the shortest path tree or source tree. DC flag is interesting. D means it's a dense mode, right? Dense mode is enabled. We are using dense mode. And C means what? Let's see, what is C? C means connected. C means that we are directly connected to the host. R2 is directly connected to the host, right? So R2 has been forwarding the traffic on which interface? On its Ethernet 0 slash, sorry, wait, where has it been forwarding? It's been forwarding on the 0/3 interface. Yeah, that's correct. R2 has been forwarding on the 0/3 interface. And then you see on the 0/2 interface it has pruned. Why? Because R3 doesn't want it. That's why it has pruned along this interface. Got it? Let's see on the last guy, which is my R3. There you go. On R3 I can see similar fashion, right? So I have 192.168.1.1. Everything is pruned, right? There's only one interface and that is 0/2 and it is pruned over there because I really don't want it. Got it? The other interesting thing is you see some flag called as A flag here, right? Also wait, I think there was another flag which I forgot mentioning, the PT flag. P means that the traffic has been pruned and T means that it is part of the tree, right? Because the source tree or the shortest path tree. But the interesting thing is the A flag. We never saw this A flag before. What is this A flag? A flag basically means that it's, if you go top, I think it should be mentioned here somewhere. Yeah, candidate for MSTP advertisement. So what it means that, so you see between R2 and R3 we have a subnet here, right? 192.168.23.0. Right now there is no host, but what if there was a host in this subnet 192.168, right? Imagine there was a hub here and we connected a host. So in that case, who would be forwarding packets to that host? Will R2 forward or R3 forward? So there is some kind of an election done here, right, for every subnet. And looks like in this subnet between R2 and R3, or R3 won the election, and that's why you see the A flag visible, right? So in case in future if you put if you had a subnet here and you had probably a PC here, then R3 would have been the one who is forwarding the packets to that particular PC. Awesome. So all of that is pretty good details. Now the last part. What if there is a change in our network, right? For example, let's say we have one more host, right, which is H3. We want H3 to join the particular group. Let's go and do that. Right, so let's say we go to Ethernet 0/0. This is a change in the network, right? What is the change? We want our H3 to join the network. Before pressing enter, what I'm going to do is I'm going to enable debugs on all the other guys, R1, R2, R3. Let me do that. Let's enable it on this guy too and on this guy, right? So I've enabled debugs everywhere. So what we are talking about now, the last part, where we are trying to understand what if there is a change in the network, right? So there is a change in the network, that is our H3 is trying to join the multicast group. So what do you think would be the change in the network in such a scenario, right? So because R3 now H3 will send a join, R3 will need to communicate this upstream route to the upstream routers, telling that hey, it also needs the multicast stream, right? So it is obviously going to pick the path. In this case, it's going to it'll have to unprune, right? It had pruned earlier, right, along these two paths, but now it's going to unprune, right? So for unpruning, right, we have to use a separate message and it's called the Graft message, right? So R3 is going to send a Graft message to the upstream neighbor, right, and the interface will be placed in forwarding mode immediately. In this case, looks like the easiest way to reach our source is basically going to be through R1. Otherwise, it'll have to go through multiple hops through R2, right? So it's going to send the unprune or Graft message along this direction, and we should be seeing that. Right, so I've enabled debugs everywhere, which is good. So what we'll do is we'll go to my H3 and let's hit the button here, and we should start seeing first on R3. We should start seeing some cool stuff. Let's give it some time. All right, let me try that once again. I think sometimes some of these interfaces play around, so let's try that again. So I'm trying to join 239.1.1.1, and there you go. I can see the Graft messages going now, right? So this is what I was saying. So whenever there is a change in the network, right? So the Graft message can be used to kind of unprune a pruned interface. So here you can see the Graft message is getting built, right, for 239.1.1.1, and that's basically going towards there should be a Graft message towards 0/0, I believe. I see yeah, over here, right? So we have a Graft message going towards Ethernet 0/0, right? And you should basically see that on this guy as well. So you can see the join list here. So now 192.168.1.1 and this Ethernet 0/0 has joined, you know, the SPT, right? So those logs can be seen, and finally, you know, there is what you call as a Graft acknowledgement is also sent along the Ethernet 0/0 towards your R3. Not sure if I have captured the Graft message, so let's check that. Do we have the Graft message here? Yeah, there you go. See, we have the Graft message and the Graft acknowledgement. This is how the packet actually looks, right? The Graft message is from R3 to R1 and the acknowledgement from R1 to R3, right? So that being said, now if you go back and check your you know, multicast routing table, let's go and check that. So you should see some cool stuff here. You can see the Ethernet 0/0 also has turned forwarding, right? Because we are forwarding it along that interface as well now. Earlier it was not, this was pruned, but now it is forwarding, right? So pretty much the same thing. Maybe we can check this on my R3 as well. And we should have the 0/0 interface is the incoming interface, right? Because our traffic is coming from where? From the server. It's coming along the 0/0 interface, and that's why it's the incoming interface. And 0/3 is the outgoing interface towards the destination. The last thing which I want to show you is link failures, right? What if there is some link failure in your network, right? What would happen? So let's say we go down to my R1 here. Right now we know that the 0/ which one? Let's say, I don't know, which one should we shut down? Probably the one below, right? Let's shut that down. So right now you know that the traffic is actually flowing along 0/1 and 0/0, right? It's coming down and it's going like this. So let's shut down the 0/0, right? To kind of simulate a link failure, right? Maybe there was an issue with the cable or something. We shut it down. So as soon as you shut it down, you can see the PIM neighborship went down, right? The PIM neighborship will go down, and there will be some messages popping up here. Let's see what is happening. You give me a second. Right. So the interface went down on R1, but on R2 you can see some stuff has come up, right? So let's see. So there's a bunch of things here. Okay, so what happened on R2 is R2 wanted to prune the Ethernet 0/2 interface, right? Because of the change in the network, right? So R2 is asking, should I prune 0/2, right? But then it got a Graft message on, I think, where did the Graft message come? I think it's not visible here, but it should have received a Graft message, right? And that's why it is sending a Graft acknowledgement to R3, because for R3 to reach the source, there is no other path now, because this interface is down, right? So R3 should be, you know, the only way to reach the source will be via this interface now, right? So R2 wants to prune the interface, but receives a Graft message from R3 requesting it to put that interface on the forwarding state, right? So that's why you can see the join list here, and you should see the same logs on my R3 as well, right? So it has pruned the 0/0 because that interface is down, and yeah, that's mainly it. I mean, let's look at the ping. Is the ping working? Yep. Look at the ping. So you can also look at the fine change here, right? So till here you can see the ping was only happening to 192.168.2.2, right, till here I believe. And once the 3.3 came into picture, which is my H3, you can see even that guy is also sending your ICMP reply, which means the ping is working. The ping which we had started on S1 as a multicast stream, it is being received both by H2 and H3, right? Even though you can see there was a gap here, which means this was the time when the interface went down. So it took some time for the reconfiguration or convergence to happen, but once it happened, you can see that flow continued, right? We can also probably see on this guy, because now it would have changed, right? We can compare the output, right? So here you can see above we had the incoming interface as Ethernet 0/0 for this 239.1.1. Now the incoming interface has changed to 0/2. This is the incoming interface, right? So PIM is like very, let's say, it can sense the changes in the network, right? Because of all the hello messages, keep alive messages which are flowing, right? The PIM hello messages, right? Once you stop hearing the hello message, because the link goes down, the neighborship is taken down, and then it will try to reconverge, right? And when it's trying to reconverge, it will try to figure out which are other interfaces from where I can reach my multicast source, and it will try to build a new tree. Now the tree is basically from starting from R1 goes to R2 and like this, and also from R1, R2 and R3 and goes like this, right? Because we have two paths, or we have two destinations, right? So yeah, so that's mainly your PIM, right? We talked about a lot of things here, mainly with respect to dense mode. We talked a bunch of things here. We configured the PIM mode, right? We talked about the workflow, about how the whole system behaves as soon as you enable, as soon as you get your host to join the particular group, as soon as you pump the traffic from here, what are the changes which you see, right? And we tried to analyze the outputs of the routing tables as well. We talked about how the tree is formed, right? The shortest path tree or SPT is formed. And finally, we talked about two interesting things, which is the graft message and the link failures. Graft messages whenever there is a change in the network, like someone is joining your network, a new host is joining your multicast group, then the downstream routers will send the graft messages to the upstream routers to unprune the interfaces. And whenever probably there is a link failure happening, right, the dense mode, the RPF changes, right? In this case, whenever an interface goes down, the RPF basically changes, because now the OSPF will reconverge first, right? And as a result of that, RPF changes, right? And now the RPF will be pointed in this direction from R2 towards R1, because that's the only path to reach R1. So and then the corresponding changes are seen in the multicast routing tables as well. So thanks for watching, guys. That was mainly your PIM dense mode.